Big enough.
Neither with the
Should be
with
great.
the
I figured
the skin would.
we got some limit there in working for it. So it's just a short step from this to that.
Okay, let's get started. Let me have your attention. Get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is Mr. Syd Ball. Syd is a senior staff member of the Oak Ridge National Laboratory. He's been there since 1957. He's really young. He started when he was quite young.
I was in grammar school at the time.
But more importantly, he has been and continues to be a longtime friend of this department, going all the way back to 1957. We've been collaborating with Syd and people that work with Syd at O&L for almost 50 years. A little bit about Syd's background. He was BS in electrical engineering from Yale University, and then he attended ORSORT. And for you students, ORSORT stands for the Oak Ridge School of Reactor Technology. And before we had nuclear engineering programs in the United States, which all came about in the 1957, late 50 time frame, we had ORSORT. And that's where people came to get their graduate education in nuclear engineering, and in particular reactor physics. There was another similar school at the Argonne National Laboratory. But we are indeed pleased to have Syd with us today. The title of his presentation is the Modular High Temperature Gas Cooled Reactor, MHTGR. We used to say MHTGR with a C in there. We don't do that anymore. And it rises again. And so, ladies and gentlemen, please welcome Mr. Syd Ball.
Thank you very much. I noticed on the flyers I was Dr. Syd Ball, and I thought I was going to get an honorary degree out of this, but Lee is stingy today. He's not going to do that. So I'll have to stick with the Mr. I understand that most of you folks work mainly on light water reactors, so we're going to diverge a little bit and get into the high temperature gas cooled reactors for those of you who are not terribly familiar with them. Some of you I know are familiar with them, but you just have to bear with me. The outline is pretty much what's going on in the HTGR world. There's some operating HTGRs, and there's some very promising designs in various stages. I'll talk about them. And then we'll get into some of the fundamental characteristics of the MHTGR, particularly looking at the differences between the HTGR and the light water reactors in terms of safety, operation, accident characteristics, and then a little bit at the end on environmental and maybe proliferation. And last time I used one of these things, I had it going out with the squirrel, so you'll have to bear with me if I hit it too many times. Okay, what is the modular HTGR? Well, there are a lot of different designs floating around. I was on an IAEA committee recently that looked at the safety and licensing characteristics, and we decided we'd come up with some kind of a generalized description of them. First of all, they have high-quality ceramic coated particle fuel, and we'll talk a little bit more about that later. Ceramics, you know, are good for high temperatures. That's one of the nice features. Single-phase coolant, which is helium, with no heat transfer limits. In other words, the helium isn't going to boil any more than it already has, and it doesn't change phase while it's in the reactor, which is nice. Post-shutdown decay heat removal can be done by a passive system called the reactor cavity cooling system. In other words, no switches, no operators, no motors needed. It just does its thing according to what Mother Nature has ordained for it. And the design features a combination of a low core power density, at least a factor of 10 less than what you have with most LWRs. A large heat capacity in the large ceramic graphite core. High thermal conductivity, sort of high, right? But a large temperature safety margin. In other words, there's a big difference between the temperature, maximum operating temperature, and the temperature in the core where bad things might start to happen. So what we do, we look at the long time response for a loss of force circulation accident. In other words, at time zero, you assume that all your cooling, all your convection cooling stops. Some cases, you lose your high-pressure helium coolant, and you watch what happens. And there have been several courses that we've given to ANS and to NRC, and one of the things we do for these long-winded courses is we say at the beginning of the course, let's start a hypothetical design basis or beyond design basis accident. And then we watch the accident progress as time goes on during the week. And if we start on a Monday morning, sometime around Wednesday noon or early Thursday, you get to the maximum temperature where you start worrying. So the time scale of the accident concerns is much different from what you have with other reactors. Also, negative reactivity coefficient, plus this large margin between operating and potential failure temperatures, allows it to accommodate reactivity insertions without problems. So what are some of the implications of these safety features, the inherent safety features? First of all, it simplifies the design because you don't have to have as many hotshot safety systems. You can imagine if you have a beyond design basis accident and start worrying about it after a few days, a few milliseconds in your scram time is not going to be a problem. So what it does, it reduces your dependence on the active safety grade systems. And one of the designs, one of the goals is to not have any safety systems, safety grade systems, which makes it a lot less expensive. I'm not sure if this is the South African design, which I'll talk about more later. I'm not sure if they've actually attained that, but they're not quite finished with that. Standardization, prefab, modularity should simplify the certification process. Now, if there are any NRC people here, please excuse me, but what these features tend to do is get the NRC people all excited looking for new and wonderful ways to dream up accidents. And so I'm not sure it ends up simplifying the certification process of the licensing. Okay, applicability of the probabilistic and the risk-informed decision-making. It's a different type of animal with this thing because your ultimate safety is determined by low probability, very low probability initiating events. In other words, if you have really no problem to worry about if you lose all your cooling and all your coolant, that's a pretty bad event. So what you have to do in order to get into really serious situations where you lose where you fail some fuel, you have to have a very, very bad severe accident, very low probability. Another nice feature when you're doing simulations of these accidents, which is what I tend to do for pay, is it's easier to model the serious accidents. The core doesn't change geometry. You don't have to worry about departure from nucleate boiling and all the tricky stuff. It's a lot easier, and that's why I got into it. I like easier problems. Okay, over the years, there have been a number of HTGRs. There are, of course, a number of gas-cooled reactors still operating over in England, but they're not the high-temperature variety. That's a distinction. But in the late 60s and early 70s, there was a Dragon project in the United Kingdom, the AVR over in Germany, Peach Bottom 1 in Pennsylvania was a USA design. Fort St. Vrain was USA. Peach Bottom was very successful. Fort St. Vrain wasn't. The THTR, Pebble Bed over in Germany. And all these things, these programs ended in the very late 80s. What they led to was a HTGR technology program in the field of materials, components, fuel, core, plant technology. And there were all sorts of good developments that led to what we came across with in the 80s, late 80s, is the modular HTGR concept. And I'll get into that. The first concepts were steam. They had a steam cycle. This is a reactor and a steam generator. And then we went to the GT-MHR for the prismatic type. That's a gas turbine modular helium reactor. And that's currently favored in some design schemes. There's a picture that the General Atomics people. General Atomics is one of is the vendor for the prismatic or the GT-MHR type of machine. They show the year. This is the year from 1967 to 1985, and these are maximum accident core temperatures. Now, of course, you can have higher temperatures than this, but these are for let's say beyond design basis, but not really wildly crazy assumption accidents. Peach bottom, the temperatures would get above 2,000, and the fuel failure would be a problem. Fort St. Vrain, likewise, the large HTGRs would go even higher. But the design of the MHR, the modular helium reactors, are such that you can lose your coolant and your cooling and still not fail the fuel. These, of course, had plenty of safety systems to keep the fuel from going to those temperatures, but they weren't inherently safe, like we call the modular. Okay, there are two operating modular type HTGRs in existence right now. One is called the HTTR, High Temperature Test Reactor. It's run by Japan Atomic Energy Research over in Ori. It's a 30 megawatt device. It's prismatic fuel, high temperature helium. Comes in this pipe here, flows up typically around the side of the vessel to cool the vessel with fairly hot gas. Then it turns around and then goes down through the reactor core. It's a cylindrical core, and its main uses are to do research for high temperature process heat designs. The outlet temperatures of the coolant, they have two modes. One is 850 C and the other is 950 C. So they're very hot. The other operating machine right now is called the HTR-10. It's a 10 megawatt reactor in Beijing in China. It's a pebble bed design. By the way, you might want to pass this around. That's a real pebble. It doesn't have fuel in it, though, I don't think. So, it's hard to tell without breaking it open or weighing it or something like that. Anyway, this is very much like the pebble bed design, except a bit smaller. It's just 10 megawatts thermal. The helium comes in a concentric pipe in the center. Okay. Will it change if I use this? Okay. All right. It comes in and then up along the side again and then down through the core, cylindrical core. The pebble beds have the feature that you can constantly refuel them, online refueling, so you don't have to shut down for refueling. This has a steam generator hooked to it, a little 5 megawatt steam generator, and they have plans to change that out for a gas turbine. They like to keep up with what the rest of the world is doing. When they designed it, steam generators were the thing, and then we switched to gas turbines. But they have a very nice, aggressive program, and they run some interesting safety tests. I'm on a IAEA committee where they done some nice benchmark problems for us, including rod withdrawal. You lose your coolant flow, withdraw your rod, and watch the thing perform for you. Okay, this is a picture of the design of the GTMHR. It's a 600 megawatt thermal job. It's the one that Department of Energy and NNSA, the National Nuclear Security Agency, is working with Russia on the design. That's my main project right now. We have about 600 Russian engineers working on the design. It's a big project. It's not as well funded as we would like, but it's going along pretty well, except maybe we're a little slow on the fuel development, but the rest of the development is going quite well. This is another case where you have the coolant gas coming in the inside of a concentric pipe, flows up around the side of the vessel, keeps the vessel cool, and flows down through the core and out into this power conversion system, which consists in one big monolith about, well, I think the latest height is like 23 or 24 meters high. There's a turbine here, compressors, 2 compressors, recuperators, and coolers down here, and a generator up there, all within the pressure boundary. I'll show a little more detail on that later. Okay, this is a layout of the GTMHR that shows the core is annular. The red thing is the active core. There are 102 elements stacked 10 blocks high. The helium goes down there mostly. There's a little leakage flow through the center and side reflectors. But the reason for the annular core is that it does better in what they call a conduction heat up or conduction cool down, depending on where you are in the accident. For a given power level, your maximum temperature with no coolant in the core is a little less, significantly less, but enough to go to all this trouble with an annular core than it is for a cylindrical core. And also another advantage is when you have control rods around the side, your active core is closer to the control rod, so you get better control than you would if the control rods were here and you were trying to control neutron behavior in the middle. Okay, this is another picture of the GTMHR, the reactor and the power conversion unit. The reason I wanted to show you this picture is, you see, the reactor is in a cavity which is below grade or below ground. Here's the ground level right here, and there's a 6-foot slab of concrete above it. So it's pretty well protected from whatever above, and it also has limited access to fresh air. And this is a big concern of the regulators and other people who are nervous about having this look like a charcoal burner. If you don't have a lot of access to fresh air, there's just so much air that can oxidize your graphite. And I'll show you some studies that we've done looking at that concern. Okay, here's a picture of the fuel. This is, of course, not the scale. This is the smallest element over to the largest element for the prismatic core. This is like 1 millimeter in diameter. In the middle, for the commercial version of the GTMHR, this is a uranium oxycarbide, about half a millimeter in diameter. And then there are layers, protective layers. There's a porous carbon buffer, silicon carbide, which retains the fission products, and then pyrolytic carbon on either side of the silicon carbide. This is a very tough fellow that tends not to fail at all unless you really mistreat it. This shows like a bunch of the particles for this design. They're put into compacts. These are a guy's fingers. They're about that big. And then they go into fuel elements. You can't see it. Sorry about that. This is a chair. It's about 3 feet high and 14 or 15 inches across the flaps of a hexagon. Okay. We mentioned the fuel and how it withstands high temperatures. The fuel is called triso fuel because of the, I'm not sure what triso stands for. We looked that up and couldn't figure it out. But there are 3 main layers. That's where the tri comes from, obviously. But anyway, you look at the fuel failure versus time at temperature. And the scale here, for those that are challenged a little bit, this is 10 to the minus 8, minus 6, 4, 2, and 10 to the 0. This means that they'd all failed, okay? And this is 1 in 10 to the 8th failure down here. Okay, if you, this is a heat-up test on some German fuel, and the time is 0 to 500 hours, okay? So if you look at this fuel and say, we'll heat it up to 1600 degrees for, it's like about 150, 60 hours, you get some failures. That looks like about 0.5 times 10 to the minus 6. Then if you heat it up to 1800 C, the curves jump up. The dashed lines are what you predict with a model. It's called the Panama model. It's one of the better fuel performance models the Germans did, mainly. Germans and Paul Kasten. I don't know if you remember Paul. He was a professor here a long time ago. So you see that the thing can sit at 1600 degrees for quite a while without failure. The failure fraction depends on the irradiation temperature and on the burnup as well. Oops. Okay, this is the other major design besides the GTMHR that is of quite a bit of interest because the South Africans are in the process of putting it together as we speak. They've gotten approval from their government to go ahead with it back in May. I got an email from their chief engineer guy a couple days ago who said, we're waiting on the money people to come forth with the final bit of money approval. So, you know, I hope that doesn't bode poorly for the design. In this case, you have a different type of power conversion unit. You also have a vessel for the reactor. Instead of one monolithic power conversion unit, you have several other vessels that have compressors and turbines in them, and I'll show you a schematic later. But some of the characteristics are it's 400 megawatts thermal as opposed to 600, 165 megawatt electric. It's a little higher pressure than the other. It's 9 megapascals instead of 7. The outlet temperature is 900. The other one is 850. The efficiency is 41% as opposed to about 47 or 8% in the other one for various reasons. This is a picture of the vessel. Just to give you an idea of the scale of this is 30 meters high, this vessel. So it's quite long and skinny. Okay, this is a schematic for the PBMR. Again, the flow is down. The outlet flow goes through a high pressure, then a low pressure turbine that drives the 2 compressors, Brayton cycle. There's a third turbine, which is called the power turbine, which powers the generator. Then it goes down through a recuperator, some other stuff. I won't get into that. This is the startup blower, which they use to get the thing started, obviously. Then the pre-cooler, compressors, intercooler, compressor, and then back through the recuperator. And there's some very interesting control problems, but they have worked them out quite well. They have a real nice test unit. They call it their micro model, which is their micro model is about as big as this building, but they were able to predict the behavior and the controllability of this quite well. This is a plan view of what they call the 8-pack. There are 8 units stacked together to give you an electrical power output about the same as you would from one of the big new LWRs. The interesting thing, or one of the interesting things about it, is that the footprint of this thing is less than what you have for the single unit LWR. Okay, here's the fuel story for the PBMR. We go from right to left for the in size here. This is the kernel. They use uranium dioxide instead of oxycarbide. The triso particle looks about the same. You've got the kernel and then the buffer layer to absorb the gases, fission gases, then the inner and outer pyrolytic carbon layers surrounding the silicon carbide layer. These things, instead of going into these little compacts, go into a pebble, size of a racquetball, which should be circulating. Hey, there you go. These are in a graphite matrix in the center. There's a 5mm graphite layer around the edge, and then there are a bunch of these spheres. I think the number is something like 350,000 of these things in a core, and about 1 billion of these little triso particles. So there are a lot of little containment vessels to keep up with in this design. There are other ongoing MHTGR programs. You've probably heard of the Generation 4 study that the Department of Energy is working on. The very high temperature reactor, which is now called the NGNP, Next Generation Nuclear Plant, is part of it, and I think it's still the lead of the several of the Generation 4 that were chosen by the committee. It has either a Brayton or a hydrogen production function, or both. The latest design of the plant that I saw has both, which I think is a mistake. But we won't go into that, especially not on primetime TV over there. The GTMHR plutonium burner, this is the one I mentioned earlier. That's the project I'm working on. It burns excess weapons-grade plutonium fuel in Russia. We have a deal with Russia that they burn a lot of plutonium, and then we burn a lot of weapons plutonium, and everybody's happier. This is part of that program. It looks very much the same as the 600 megawatt commercial version. Japan is designing another 600 megawatt thermal or 300 megawatt electric that looks a lot like ours, except the PCU is horizontal instead of vertical. IAEA has several ongoing coordinated research programs, numbers 5 and 6, which have to do with plant performance. That one's winding down. I'm on that committee. And fuel performance, which is just starting up. And those are very active and interesting committees. They do a lot of good benchmark programs. We have about 12 different countries participating in CRP5. And they're all very interested in the concept. Europeans are also very busy, along with the IAEA and some of their other programs. One of them is called INPRO. I couldn't find out too much about that. I just know that they do have a pretty good budget for development over there. Okay, we'll get into some of the characteristics of this thing. This shows the GTMHR, and it shows what isn't part of it. In other words, it doesn't have the steam cycle stuff that you need for an LWR. It doesn't have all the condensers and the feed water heaters and things like that. So that supposedly simplifies it, and as they say, improves plant availability. It improves plant availability if you keep your power conversion, your Brayton cycle turbine working, turbine and compressors working. I think one of the main reasons there's been more interest in the gas turbine cycle for HTGRs is the improvements that have come along in gas turbines lately. You know, there's a big effort, and there's lots of gas turbines, not just the airplanes, but other power units. Okay, this shows a comparison of the type of the sort of plant efficiency you get. This starts at 30 and goes up to 50% efficiency with the steam cycle versus the Brayton cycle, the gas turbine. And of course, the people promoting this are happy to conclude that you can get close to 50% efficiency with the gas direct Brayton cycle versus what you get with the steam cycle. This bottom, this is in Fahrenheit here. Pardon me. We get confused a little bit. 1600. You guys are all metric, I guess, now, aren't you? Both. Both. Oh, well, very good. Okay, this is about 850 C here. This is the design outlet temperature of the GTMHR. Okay, a friend of mine, Jim Kendall, who's retired now but worked for the IAEA for a while, made what I thought was a neat comparison of the light water and the MHTGR core emergency heat removal task. With an LWR, this is a PWR, I guess, pin diameter about 1/2 inch, and some of the fuel is above 2200 F, which is the circ water reaction temperature. So what you have is something that's 2200 degrees F, about an 1/8 of an inch away from the cladding. So what you need to do is be very, very good about keeping this 1 acre of clad surface area under control. And they, of course, are very good at doing that. They have excellent heat removal properties, high velocity or nuclear boiling, whatever, to keep the clad safe. But if you lose that feature, you can get into trouble with the Zerk water reaction in a hurry. Contrasted with that is the MHTGR. Peak fuel temperatures at full power operation are about 400 C below the temperature where one might get concerned. In other words, below this 1600 C. And so in a design basis accident, the fuel temperatures reach the maximum in a few days. So you just look at the difference in the anxiety level of the operators or whomever are worried about having fuel failure. Okay, this is a topic dear to my heart, core thermal hydraulics. They're quite different, as you might imagine from what I've already pointed out. The gas thermal hydraulics, slower and easier to predict, single-phase coolant, and mostly benefits, but there are some problems. And by the way, the thermal hydraulics, every once in a while, some English major comes at us with hydraulics. Well, that's water, you know. But and it's funny in a way. Just about every gas-cooled reactor in history has had water in the core, inadvertently. So we're hoping that the GTMHR with its Brayton cycle, for which the water pressure, there's no steam, but the water side pressure in the coolers for the Brayton cycle are always kept at a pressure lower than the primary, unlike the steam cycle where the steam pressure is steam and water pressure are a lot higher than the primary pressure. Okay, so hopefully the hydraulics doesn't refer to water. That's supposed to be a joke. Thank you very much. Okay, these are some of the attributes. As I mentioned, the primary helium coolant is downflow. This is different from the LWRs. It's an annular core rather than cylindrical, typically. A big delta T inlet to outlet. This is another thing that brings up some interesting considerations. The difference between the inlet and outlet temperature can be about 400 C, which is about 10 times what it is for a PWR, roughly, I think. And so what you have is the possibility that, you know, if this temperature gets out to the vessel, you have one whooping gradient in the vessel. Typically, though, it doesn't, it says here. Slow, big heat capacity, lower power density, and I've said that before, big margin. This is another interesting thing, the outlet temperature non-uniformity. If you have 400 degree difference between the inlet and the average outlet temperature, some of it, the stuff going down through the active core gets heated at least 400 degrees. The stuff that seeps through the side reflector and the center reflector doesn't get heated much at all. So you have hot and cold gas both going into the outlet plenum at the bottom, and this leads to fluctuation and mixing concerns. Okay, the high temperature helium is ideal to go into a direct Brayton cycle. If you had another medium like molten salt, like Charles Forsberg is jumping up and down about now, you have to, if you want to do a Brayton cycle, you got to do an indirect cycle. You can't, well, it can't do a Brayton cycle, okay, with a gas cycle directly. Another interesting thing about the control, if you're varying the power level in one of these things, they don't, well, the way they do that is to vary the inventory of helium in the primary system. They bleed it off into storage tanks or put it back in. This varies the density, and the reason they do this is the turbines are much more efficient if the gas going through them is a constant velocity at the lower power. So they can keep their efficiency up even with the lower power this way. Another interesting thing, system discharge temperature. These funny little things, these are supposed to be arrows, but I guess Bill Gates intercepted me here. The discharge temperature, in other words, the heat sink temperature for the Brayton cycle is just about ideal to use for flash desalination or district heating. If you want to do desalination with an LWR, you have to lop off the back end of the low pressure turbine in order to get temperatures high enough to flash water reasonably. Okay, graphite conductivity. This is an interesting factor in calculating what goes on in a reactor core, a gas reactor core. This plot here, which is probably not too visible, shows thermal conductivity from 0 to 60, and these are units of watts per meter per degree, Kelvin, per Kelvin. And this is a function of dose for various irradiation temperatures. The thermal conductivity drops precipitously. Oh, okay, look at that. Okay. For the case where it's a low irradiation temperature, it drops quite a bit for higher temperatures, but not as much. So this is quite a difference in the conductivity. This other plot is similar. This is same kind of thing, thermal conductivity, same unit, 0 to 60, and 0 to 2000 Kelvin. For the irradiated graphite, it starts at about 10 and goes up to 22 or something like that. For the unirradiated, it decreases with temperature. And what you need in your accident models for these things is an annealing model, because if you start with a low conductivity, some graphite that's been irradiated at a fairly low temperature, and then you heat it up, it anneals, and the conductivity increases, which is helpful. Okay, another interesting point, I think, since this is my business, I have to think it's interesting, is the thermal conductivity in the pebble bed. Now, you see these pebbles that you passed around. That's the bed of the reactor. So what's the effective conductivity of a pebble bed? Well, if you just relied on the contact between the pebbles, there wouldn't be much contact. So this curve here, which shows conductivity, different units, this is a factor of 100 less than the other graphs, and this is temperature in C, just keep you on your toes. It starts out at near zero and then goes up with temperature. This is 1500 C here. You tend not to get into this range much. But you see it's mainly determined by the T to the fourth radiation. Okay, helium, a great coolant. It's transparent to neutrons. You can lose all your pressure and it won't affect the reactivity. It's inert. But like other gases, its viscosity increases with temperature, about the 7/10 power of absolute temperature. So what you get with a higher temperature is an increase in the friction factor and a decrease in the heat transfer coefficient. And if you look at stability for heating, for cooling down hot systems, this is just the opposite of what you want. You can get into what's called laminar instabilities if you're not careful. So you have to design to avoid that. Just to give you an idea what the temperature profiles look like, this is the PBMR, the pebble bed South African plant. This is the maximum temperature from inlet to outlet, maximum fuel temperature, and the average fuel temperature from inlet to outlet on 100% power. This goes up close to 1100 C. The peaking of a pebble bed, since you're just running fuel through it, is pretty much out of your immediate control. You can, with the prismatic, you can load the blocks like you want and have that difference. Okay, this is the sort of the same kind of thing for GTMHR, the prismatic fuel. This is temperatures from the center line of one of these little capsules or cartridges. This is the fuel. This is an assumed gap. This is a graphite matrix in that big block, and this is the coolant temperature in the bottom of the core. You see there's not much delta T, but it's a higher temperature, say maybe 1200 C maximum, versus the middle of the core where it's maybe 1050, bigger delta T from here to there, but lower temperature. It hasn't heated up quite as much. Okay, the decay heat removal paths. The decay heat removal is one of the things you really need to do well if you have one of these long-term accidents. Under normal conditions, if you shut down, you can use your power conversion system. Just run it. There's an active shutdown cooling system you can turn on if this thing isn't working. It's typically not a safety system, but there's a little heat exchanger and blower at the bottom of the reactor vessel. You run that, and that'll cool down the reactor in pretty good stead. Now, if that doesn't work, if neither of the top two work, you rely on your passive reactor cavity cooling system, which is typically either a water-cooled or air-cooled loop of it's like a radiator, except it goes the other way. It goes down around the reactor cavity, and that operates as a natural draft system without any switches or whatever all the time it's operating, by the way. If your RCCS fails, you get conduction and radiation to the ground and the surrounding structures. Key points for the RCCS. Cooling panels surround the reactor vessel. It's got a dual function. It has to keep the vessel concrete cool during a normal operation, but you don't want it to remove too much heat or you have a lot of parasitic heat losses. So it's sort of a give and take there. In accident conditions, it provides the ultimate safety heat sink. Vessel to panel heat removal is mostly T to the 4th radiation. It's for most cases in accidents, it's at least 80% of it is T to the 4th. The rest has to do with the air convecting in the cavity. Panel heat sink, yeah, I mentioned that. Completely passive in the accident mode. Some of them have motors and things that drive it during the normal operation, but if you lose power, have a site power loss, it goes into the natural convection mode. Conclusions about thermal hydraulics. Straightforward, helium coolant, variable properties. You see what you have to deal with worrying about what is the real conductivity of graphite or the core conductivity in a pebble bed. A lot of uncertainties there, but what you have to work with is a generous margin between your operating temperature and your fuel failure temperature, thanks to the ceramics. Some safety features help maintain the core conditions and configuration. There are some cases where you might have a configuration problem, and that's with a lot of air ingress, and we'll talk about that in a bit. Comparison of nuclear and physical dimensions. This is a favorite slide for the physicists. This is the actual physical dimension of a GTMHR 600 megawatt compared to an LWR 3,000 megawatts thermal. See, this is a good bit taller and bigger. But the nuclear dimensions for the LWR a good bit bigger than the GTMHR. Now, what do I mean by the nuclear dimensions? Well, it has to do with how much the neutrons bounce around once they escape from the particle. They bounce a long way in the graphite core, so nuclear-wise, it looks a lot smaller. You can get a better representation with a point kinetics model with this thing than you can with that thing. That's very helpful, again. Reactivity behavior during operating cycle. With a pebble bed, with loading the pebbles constantly, whenever you need more reactivity, you just put in more fresh fuel. Your excess reactivity doesn't have to be very high. It can be just enough to maneuver with. With the GTMHR, where you have to shut down to reload, you have to put in a lot more reactivity to keep from having to reload all the time. But and this is what you would have to have. This is 1.14 for multiplication factor versus down to 1.0. You'd have to have quite a bit if you didn't have burnable poison. So the GTMHR designs, in order to keep from having a whole lot of excess reactivity, uses either uniformly distributed poison or this is called lump boron. So there is a way of getting around that problem for the prismatics. Okay, accidents. I need to skip along here. The one kind of accident is called the pressurized loss of force circulation. And in these, you typically worry mostly about the vessel temperature. The peak fuel temperatures are not limited. I'm going to have to go a little faster here. And I apologize for this. I didn't think it would be quite so invisible. But what this shows, this is our code output here. This is maximum fuel temperature versus time, and this is about 1 week in duration. It shows the temperature going up to 13. 35 hours. It also shows the peak. This is axial profile of the maximum fuel temperature from the inlet or the top to the bottom outlet. And you notice after a long time in the pressurized, the peak fuel temperature rises up to the top, like mid a chimney. So you get a shifting in where your peak temperature is. This is a typical calculation for a PBMR for a depressurized loss of forced circulation. The peak temperature peaks out a little less than 1600. This is a PBMR calculation by the PBMR people. This shows the profile from the center of the core out to the reactor cavity cooling system for the GTMHR, the prismatic one, at the time of maximum fuel temperature. You see the central reflector is pretty hot. There's a gradient in the annular core, and then as it goes down through the reflector, it cools down, and then over to the vessel and the cavity cooling system. This is one of my favorite plots. It shows what happens if you have an atlas, in other words, a no scram. At the same time, you have a pressurized loss of force convection accident. The first part of the accident, it shuts itself down because of the rise in the average nuclear temperature. And it goes along for, in this case, a little over 40 hours before it goes recritical again with the xenon poisoning burning out. And then it goes up to a little over 1600 in this case. And then what happens is the operator decides he can restart one of the coolers. And this shows what happens to the maximum temperature when he restarts the cooler. And what I call this, it shows the effect of selective undercooling. Remember that characteristic of helium where the friction factor increases with temperature and the heat transfer goes down? Well, when you put a little more power in it and put a little cooling in, you get the wrong effect. The hottest channels get the least flow. This shows some of the characteristics from ARCO. This is the pressurized loss of force circulation in atlas. One of the interesting features of the recriticality for these gas reactors is when it does go recritical. I don't know if you can see it. It goes. The power jumps up and then it oscillates. And this is maybe not a numerical oscillation in my program, but if you look at any of the tests that have been done, they did it with the AVR in Germany, and they did it just recently with the HTR-10 in China. You get that same characteristic oscillation. Okay, we're into the air ingress thing, and I'll try to get through that in a hurry. The Japanese did some air ingress experiments on a rig. If you have a break in the helium vessel, helium cooled vessel, it takes a while for the air, if it's just a single break, it takes a while for the air to get into the vessel in such a way that you get a significant natural circulation. And they call the several stages here. The depressurization stage, where the helium goes out. The first stage, where you have molecular diffusion of the air in the helium. And then finally, it's almost like a switch. It snaps in, you can get pretty good air and ingress flow. This is an example of one of their tests with the points versus the calculation with the straight lines. And you see after 6 days, the density of the gas in various places sort of creeps along and then all of a sudden shoots up because you get the air coming in there and circulating. And so what you have with a single rupture in a pipe and these things is a fairly long delay depending on this molecular diffusion, which is very difficult to calculate because of it's a sensitive calculation, sensitive process. So if we do a calculation of the pebble bed with air ingress with a single break, in this case we've assumed that the air doesn't really start to circulate for 2 days, fairly conservative maybe, and this is the power in kilowatts. It goes up to about 800 kilowatts of heating from the oxidation of the graphite. What it does to the maximum temperature, however, is nothing, because the air, when it goes into the bottom reflector. This is a picture of oxidation rate versus axial position, and this is the bottom. You see, all the oxidation is taking place there. The maximum temperature is not much, if any, different from, and actually it's cooler because it cools a little bit. This is an example of an experiment the Germans did where they did that kind of thing. This shows how much oxidation took place in various parts of the core. This is the lower reflector. This is the core area. You see it's predominantly in the bottom. If you have a double break such that you have, such that you have access to the bottom and the top with unlimited supply of air, you get a lot more oxidation. Sometimes that oxidation can creep up into the fuel area. So the reason you don't get a lot of problem is because the flow resistance is quite high in both the pebble bed and the GTMHR. So even if you have access to air, you don't get a lot of flow. The key, however, is to limit the access to fresh air, and that picture I showed with the cavity, the reactor cavity underground, with not much around it, I think makes the case. And one of the next things we're going to do with our model is to put in a air access thing. Okay, quickly go to the environmental impact comparisons. Thermal discharge. If you have a 50% efficient plant for a given kilowatt or megawatt electric, you get 100% increase in thermal discharge power per unit electric versus this is a GTMHR, this is a LWR. So for a 3,000 megawatt plant, you'd get 15. You can do the arithmetic. High level waste, you have to burn more fuel, so in an LWR to get so much power production. Low level waste, I'm not sure exactly why there's that much difference. I think it has to do with the fact that for low level waste you have more problems with the steam cycle. Fuel waste disposal. MIT did a study of the waste disposal problem, which is of a lot of concern. Per kilowatt hour generated, electric that is, space taken up in a repository is less than for spent fuel from a LWR. However, if you ship this stuff in a standard LWR container, you have to ship 10 times as much stuff, 10 times as many containers. Graphite spent fuel form is ideal for direct disposal. What they do for direct disposal is they just take the fuel element out of the core and stick them in a repository. You don't have to put other stuff around them. Silicon carbide is an effective retardant to migration in the long term. Okay, proliferation resistance. This is for the PBMR, and this is, again, the MIT study. To divert 8 kilograms of weapons-type plutonium from a PBMR, you'd need to divert 800,000 pebbles from the online recycle, or 250,000 for discharge of the spent fuel, or if you sneaked in U-238 pebbles, you still need 15,000 to get your 8 kilograms. Summary. High level of inherent safety, rate and cycle, good stuff. Low cost, I'm not getting into the cost stuff, I'm not a cost guy. Significantly reduced environmental impact. good radionuclide retention, and high proliferation resistance. And if you want to read more, there's the IAEA has a very good website, www.iaea.org, HTGR. So that's it. I'm half a minute late, sorry. Which leaves me no time for questions.
No, we have time. We do have time for questions. In fact, we have a question from our cyber audience, which doesn't happen very often, so let's handle this one first.
Okay.
This question comes from Dr. David Pointer, who is a staff member at the Argonne National Laboratory and a graduate of this department. He was one of Dr. Roberts' students. The question is, assuming that everyone decides that we need to build a new fleet of nuclear power plants in the U.S. tomorrow, what do you see as the most difficult challenge in selling a 300 to 600 megawatt gas-cooled plant to, there are three different categories here, to financiers, or just a demo plant to Congress, to licensing authorities, and to the general public?
Okay, what's the answer? Oh, am I supposed to?
Yeah, you're supposed to answer. You answer people first.
Of course, the finances of the HTGR are, of course, questionable because it really depends on a lot of things, including time for licensing, availability of capital. One of the nice features about the modular is that you can start building the modules and add to them as your power needs increase. In other words, for developing countries, it's especially interesting. But even for utilities where you may only need a few hundred megawatts to start, you can just add on, and you start getting capital. You start getting revenue before you build the entire plant. So that's attractive. I think my view, and one of the reasons I was really interested in this, is because I think the safety characteristics are such that it's really hard to argue that you can get a serious accident out of these things, and that should help the public acceptance. However, most of the civilians I talk to, my in-laws, for example, are most worried about the waste problem. They think the waste problem is what's going to really hurt you. And again, I think the HTGR goes a long way to solving that and the proliferation problem as well. I think it's a matter of education of the features of this thing and the politics. I think a lot of the work on the HTGR and the government development of HTGR has been stymied by the fact that the other power-producing companies don't want the competition, and they do what they can politically to keep us from getting it. So,
okay. Do we have questions from the local audience? Okay, Mark.
Well, the packaging for LWR fuel disposal is quite extreme. Could you elaborate a little bit on why there is such a difference?
Well, okay, it's a very low power density. So after a relatively short time compared to what you get with a high power density fuel, the cooling problem isn't as severe. You know, for a given size piece of fuel, and also the fact that the temperature that you can store it at could be a lot higher. I mean, it could actually go up to a quite high temperature while you've stored it, and it won't fail. I mean, you've seen the failure rates. So you can probably store this at a much in a way where you don't have to build special materials to contain it. The cooling part is easier, and the maximum temperature before you get into trouble with the stored fuel is much higher.
What about corrosion and stability?
Well, they've done some tests. I don't know how you can really extrapolate to a million years, that kind of thing. But they've done some tests on the corrosion stability of the silicon carbide and the triso particles, and extrapolate to, long enough so that it shouldn't be a problem.
Okay. I do see a few new faces in the audience, although this one has been around quite some time. And the new people here may not know that we do have refreshments downstairs on the second floor, and you have an opportunity to talk with Syd and ask more questions. But before we adjourn for refreshments, let's express our appreciation again to Mr. Ball.
Thank you for staying awake. Some of you.
Yeah. Hey. Hey.
I first a pebble.
Bring it.
All right. Thanks for the next show.